So we started looking at polarization modulated sensors in the last lecture. So we talked about using an optical source, and so if it is an optical fiber sensor, you launch that into an optical fiber such that you launch a particular polarization inside that optical fiber, and with perturbations the polarization state might change. But since your optical receiver is not sensitive to polarization changes, you need some sort of a demodulation mechanism to convert any polarization change into change in intensity, which can subsequently be picked up by the optical receiver. So today the question is, so what is this demodulator, right? So that's what we're going to look at. And so for polarization demodulation, it's quite helpful to understand Malice Law, right? What Malice Law states is that if you have polarized light, let's say you have this optical radiation coming in, and this polarizer is oriented such that it gives vertical polarization, and if it goes through some material, let's say initially this material is not perturbed, right? So you would expect that without any external perturbation, whatever incident polarization is, the same polarization you would get over here. But how do you know that you're getting the same polarization? Well, one way you could possibly do that is just like you had a polarizer here, you have another polarizer over here, okay, which we call as an analyzer, okay, and let's say it's originally oriented vertically, so it allows vertical polarization to go through, but you do a certain rotation. So you can basically rotate, suppose you put it on a mount where you can rotate that analyzer, so you can actually go through different angles with respect to the polarizer angle. And what Malice Law tells us is, if you do that, if you rotate it over angle theta, then you would essentially see the polarization, the transmitted intensity that you are looking at over here. You can call that P transmitted, right? The P transmitted would have a maximum at theta equals to 0, and then as you start rotating, it's going to start allowing a smaller component of this light to pass through, so it's going to come down and it's going to go to a point where it becomes 0, and that corresponds to the point where this is actually oriented at 90 degrees, so it's orthogonal to this polarization state. So this is actually something that happens at pi by 2, and then of course if you still keep going further, it will go to a maximum and then it go to a minimum and so on. So this is actually at pi, and this is 3 pi by 2 and so on, right? So you can essentially, by analyzing the output radiation that you have here from this medium, you can actually figure out what is the what is the polarization state at the output. Okay, now So what Malice Law tells us is this is actually a cos square function. So Malice Law tells us that P transmitted is going to be the incident power P naught multiplied by cos square of theta, where theta is the orientation of the output polarizer, which is what we call as the analyzer. Okay, so it essentially goes through a cos square function. Okay, now how do we pick up any perturbation? So if there are some perturbations that this medium is exposed to, then the output polarization is going to change. So let's say it shifts to some sort of an elliptical polarization, right? So the polarization axis is changed, and then it also the perturbation has introduced some there's some birefringence in this medium, so it introduces a phase shift between the two orthogonal components. So then you have an elliptical polarization, and let's say if this is at 45 degrees, right, then so what we expect here is as you rotate this analyzer, you're going to see a maximum at 45 and a minimum at 135, and then a maximum once again at 225, and so on. So you would basically say at pi by 4, it will go to a maximum at 3 pi by 4, it will go to a minimum, and 5 pi by 4, it will go to a maximum again, right? So you'd expect something like this. If this is your average line, then you would essentially go to a maximum here at pi by 4, and then you'll go to a minimum at 3 pi by 4, and then a maximum again at 5 pi by 4, and so on, right? So this would be the output that you get to see for the perturbed case. And by looking at this, we can make out that it's elliptical. So how can we say it's elliptical? Because of the fact that your maximum and your minimum is not as high or as low compared to your linear polarization, right? Its minimum should be 0 for linear polarization, but because in the elliptical polarization, the minimum would still correspond to the intensity in the minor, along the minor axis of the polarization, so it won't go to 0. So by looking at this, you can say that this is actually elliptical polarization, whereas you originally started with a linear polarization state, right? So you can essentially tell that some perturbation has happened, which has caused both coupling into the orthogonal polarization state from the vertical polarization to the horizontal polarization, and also there is a phase shift between that. And of course, so we talked about linear and elliptical. So what would happen if it was circular polarization at the output because of this perturbation? That would just correspond to just a straight line here, because as you rotate across a circular polarization, you get a constant intensity. So you can also tell that if it is circularly polarized, you can tell that you can tell that by looking at this transmitted power through the analyzer. So this analyzer essentially is what acts like a polarization demodulation mechanism. Okay, so that's great that we could actually analyze the polarization in a relatively simple manner. Of course, you cannot tell which-handed polarization it is, right-handed, left-handed, and all of that. So that is an issue, but not a major issue, because we are just trying to sense the magnitude of the perturbation. So when I talk about magnitude of the perturbation, you are interested in picking up, you want to understand what is the minimum limit, minimum detectable limit as far as the perturbation is concerned. And in this case, you find that the minimum detectable limit is, the case where it's linear and then it's slightly maybe tilted or something like that, so with respect to, so you're starting with this without any perturbation, and then you're slightly moving around here, right? And we see that it's not very sensitive at that particular point. Okay, so it's minimum detectable limit is determined by the operating by the operating point, which corresponds to the unperturbed polarization. Now, of course, you can make a couple of arguments about this. You can say that I can increase my sensitivity by, instead of looking at a polarizer with this oriented like this, originally I can look at something where it's cross polarized. So normally it's dark. So if it's cross polarized, that would actually correspond to a P naught sine square theta form. So normally it's dark, but if there is any perturbation, then it becomes some finite intensity will leak through, and based on that you can possibly tell what is the magnitude of that perturbation. However, even in that case, what will happen is as you increase your perturbation, it is eventually going to go to the maximum. So if you start operating at this point, right, so if you can argue that it can start operating at this point, and then you can have some sensitivity here, but even here it's not ideal. So what you probably want to do is actually have your bias point somewhere over there, so that's where you get the maximum sensitivity. However, if you are just looking at one output like this, that may not actually provide the highest sensitivity. So the idea is, can you use polarization diversity. So what is polarization diversity? Well, so now once again you're looking at perturbations to this medium. So we once again start with a polarizer, right? So light actually comes in here, it's launched into this medium, which could in our case could be an optical fiber. So the output of that, instead of analyzing just with regular polarizer, you use what is called a polarization beam splitter. So there is something called a Gland Thompson polarizer, which essentially consists of a birefringent material, so we know whenever we go into a birefringent material, especially at an angle with respect to what is called optical axis of the birefringent material, you generate what is called the ordinary ray and the extraordinary ray, and then you could essentially have an air gap over here which reflects one of those rays and lets the other one transmit, because those two are at two different angles. So you can essentially design it such that it's totally internally reflected, to the point that if you have both polarization, let's say this is the what is called the perpendicular polarization, it's because it's perpendicular to these plane of incidence. The plane of incidence is the plane that has both the incident, transmitted and reflected rays, right? So this is perpendicular polarization, and this is what is called parallel polarization. So in short, this is S, this is P, and this is S. Okay, so if you have orientation such that you're transmitting your let's say your perpendicular polarization, and you're reflecting your parallel polarization, okay, then you have basically two light beams that you can simultaneously detect. So you can put a photodiode here and a photodiode here, and you can generate a photocurrent, and that photocurrent now you can actually give it to a balance detector, and then you can essentially take the output. So that's basically corresponding to the differential output. Okay, so what exactly are we doing? We had this power transmitted curve drawn as a function of say that incident polarization. So you have essentially whatever response you are getting in this port corresponds to your cos square function, right? But the response that you get from the orthogonal port, that will correspond to a sine square function now. Right? So this corresponds to a sine square of whatever the input polarization component, whatever that angle it has got with respect to the perpendicular angle, and this is actually corresponds to a cos square function. So in terms of the current that we are getting here, let's say this is current I, if we put down that current I, that will correspond to certain responsivity of these two photodiodes. Let's call that R times the power that's incident on it, let's say is P naught. Then you have essentially cos square of phi minus sine square of phi, right? Because in this port you are picking up the cos square component, and in this port you are picking up the sine square component. So you are doing a differential detection, in which case there is no if you are picking only the cos square, then you have very little sensitivity around this, and if you are building if you are picking up only the sine square, then you have very little sensitivity here at those points. But if you are picking up both sine square and cos square, wherever this is actually not sensitive, this is you can pick up wherever you don't get much light here, you get light there, and so on. So you can actually prove that in this sort of a scenario you get the best sensitivity, and to do that, you can just basically simplify this. So that corresponds to R times P naught cos of 2 phi, where phi corresponds to the angle of the incoming polarization. So let's say the input polarization or the because of the perturbation, that output polarization is tilted like that phi is what we are tracking now, right? So that corresponds to this responsivity multiplied by the power that's incident on those detectors multiplied by cos of 2 phi. And what we are interested in is what is the minimum change in this rotation angle phi that we can pick up. So to look at that, you basically take a differential di over d phi. If you do that, then you get minus 2 times r p naught sine of 2 phi. Okay, and of course, when you look at that, so that corresponds to the slope of this response curve here, and where is that maximum? So this becomes maximum at phi equals to pi by 4, because when phi equals to pi by 4, this term within the parenthesis becomes pi by 2, so sine pi by 2 equals to 1. So that's where it becomes maximum. Okay, so what that tells you is something that we intuitively figured out, that this point here, which corresponds to pi by 4, that is actually the best operating point. So from a polarizer perspective, whatever launch in polarization is concerned, you are best off by launching a polarization like this at 45 degrees, okay, so that it has got equal components along the two orthogonally polarized directions, and then as it propagates, you see because of some perturbations, you might have some small rotation around this point. So you are biasing at phi equals to 45, and then because of this perturbation, you get say some small theta change in that, and that is the change that you are interested in picking up. Okay, so let's just try to write that down mathematically. If we bias at phi equals to pi by 4, then I is given by r times p naught cos square of pi by 4 plus theta. That's the theta corresponds to the change in polarization angle as a function of that perturbation, minus cos square of minus sine square of pi by 4 plus theta, right? And then once again, like we did before, you would say that is corresponding to cos of twice this argument, and when you do cos of twice that argument, you get basically cos of pi by 2 plus 2 theta, right? which is it can be written as minus sine theta. So this is r times p naught minus of r times p naught into sine of 2 theta, right? And for small angles, small changes in theta, theta is the deviation from the pi by 4 bias that we have applied. So for small changes in theta, sine of 2 theta can be written as 2 theta itself. So this can be approximated as minus r times p naught 2 times theta. Okay, so this is for small values of theta. Okay, so by going through this polarization diversity, now we can of course say that if you had only one port that you were looking at, you would essentially not get this sort of sensitivity. So you are better off by going to both the ports. And so essentially, if we just say because of the polarization diversity, you are having twice the sensitivity, right? Because you have this 2 theta thing. If you just had only one of these, you would have just a theta term over here. So you get twice the sensitivity, but the more importantly, in this sort of a scenario, you have zero background. So what do we mean by that? Well, in this sort of scenario, if you are biased over here, you have a very large power that you are measuring, and you're within that large power, you are trying to make some look at some very small changes, whereas in this case, and so that large power can give you a significant amount of short noise, but in this case you do not have that background, because essentially you're doing a differential detection over here. Okay, so you don't have when you're looking at I, basically you don't have a DC term over here. Whatever it's proportional to theta, so it gives you the signal with high sensitivity with zero background. Okay, so that is the key point as far as using a polarization diversity scheme is concerned. So what we have seen so far is one, we can actually do a polarization analysis at the output, and that is our demodulation mechanism for picking up changes in polarization. And two, we said if you use a polarization diversity scheme, then we can actually do this detection with even more sensitivity and zero background. So polarization diversity scheme, which corresponds to looking at both the orthogonal components simultaneously, is the way to go as far as picking up polarization changes are concerned. So that's a key way. That's the best way of demodulating your changes in polarization. Okay. Now, how can we use this for a practical application? So the question is how to use above scheme for practical application. Okay, and one such practical application where this scheme or this methodology is widely used is what is called fiber optic current sensor. So for a current sensor, essentially you need to be able to pick up relatively small amount of current, let's say 0.1 or even lesser than that, 0.01 amperes to something the order of kiloamperes. Okay, so if you are actually a power generating station, you might actually be generating something the order of kiloamperes. So you need to be able to pick that up with very high linearity. Okay, and there are conventional sensors like Hall effect sensors, which are dependent on the magnetic field that is present because of current flow in a conductor. But those have a lot of calibration issues, whereas this fiber optic current sensor has been proven to be an extremely nice way of picking up current over a very large range, like you talked about. So how does this fiber optic current sensor work? What is the basic principle for this? So that actually is dependent on what is called Faraday rotation. Okay, so you can essentially use this Faraday, basically Faraday effect to pick up these changes in current. So how does so what is a Faraday? What is the Faraday effect? Now, if you go through certain material, okay, which are subjected to, let's say, a magnetic field like this along its axis, oriented along its axis. If you come in with light, let's say it's vertically polarized light, right? It can end up changing the polarization state under the influence of this magnetic field. So your output polarization might be tilted with respect to the input polarization through this under the influence of this magnetic field. And this is actually described by, if you look at the displacement vector, right? So normally you define the displacement vector as epsilon times E, where epsilon corresponds to the permittivity of the material, which is epsilon naught multiplied by the relative permittivity of the material. But in addition to that, what you get is actually a Magneto gyration effect. So you get J epsilon naught gamma multiplied by B cross E term, where B corresponds to the applied magnetic field, cross E corresponds to the E corresponds to the electric field of your incoming light. Okay, so what that tells you is the response of the material, which is characterized by this displacement vector. Okay, the response of the medium is such that it rotates, because this is a curl B cross E that means that it's rotated with respect to the input orientation of the light. So you have a certain rotation that's happening, and that is actually defined by that response is defined by this gamma, which is called the Magneto gyration. Gyration is essentially it's like a changing the orientation. So Magneto gyration coefficient. So there are certain material which have a larger Magneto gyration coefficient than some other material, like so you have TAG material that corresponds to terbium, aluminum, garnet. That actually exhibits much higher magneto-gyration coefficient compared to, for example, glass, which is silica, right? But nevertheless, the idea is that because of this magneto-gyration, there is a change in the orientation. The incoming polarization is rotated through an angle theta, which can be defined as, in general terms, it's proportional to the magnitude of the magnetic flux density that we have multiplied by the length of that crystal, and the proportionality constant here is this V, where V is actually a representation of the magneto-gyration coefficient, and it's called the Faraday constant. So the Faraday constant V can be written as minus pi gamma lambda naught divided by lambda naught n naught, and this is actually a value that can be, like, for example, for TAG material, it's 1.16 minutes per Oersted. Oersted is actually unit of magnetic flux density, and centimeter corresponds to the length of your crystal. Okay, and so this is actually the angle. The angle is expressed in terms of minutes. Of course, you can represent that in terms of degrees or radians as well. Okay, so that is for a particular material like TAG. However, if you want to use this for glass, this is actually 2 orders of magnitude smaller. So it will work out to be like 0.01 minute per Oersted centimeter and so on, right? So it's actually a much smaller effect in glass, but can we use glass for picking up this rotation? How can we use this effect in a current sensor? So let's actually look into that. So what we can actually have is this fiber. Let's say you are making a coil of this fiber, and you are going out like this. Okay, now I am inserting this current carrying element, let's say a wire. I'm positioning the wire along the axis of this coil, and let's say there is a certain current I that is flowing through this conductor. Okay, we know that because of this current, you have a certain magnetic field. So what is going to be the orientation of the magnetic field? That is going to be along this fiber coil, right? So you develop a magnetic field around it. So how do you quantify the magnetic field? Well, you go back to Ampere's law. Ampere's law tells you that H dot dl, the magnetic field intensity dot product with the line integral, this closed line integral, that is going to be equal to the current enclosed. So you can basically do it for this geometry. You basically say this is actually H phi multiplied by, if you do a closed loop integral on this on this fiber path, which essentially has let's say radius r with respect to the center where the current conductor is, then you can just say H phi and the corresponding B phi would be like this. So H phi is going to be given by I over 2 pi r, because that line integral is going to give you 2 pi r term. So you can take that over here, and you can write this as 2 pi r. So if you are looking at B phi, that is nothing but mu, where mu is the permeability of this medium over here, mu I over 2 pi r. So the point is, according to the current that's flowing in this wire, you have a magnetic field generated. So what's the big deal? So how is this helpful for us? Well, it's helpful because now we are actually looking at the Faraday effect, right? So now we can talk about actually launching a polarization like this. So if light actually goes through this material, imagine that it's actually under the influence of the magnetic field along the axis of this fiber. So you are subjected to the Magneto gyration effect, the Faraday effect, and because of that, now you go with an output that is going through an angle theta with respect to the incident polarization angle. Okay, so theta is given by the Verde coefficient of silica, which I said is 2 orders of magnitude lower than that of tag, B phi multiplied by length. So this is the interesting point. The length of these crystals, it's typically in the order of centimeters to get let's say 45-degree rotation. Like you can possibly have some 1000 Orsteds or something flux density, and then for that, if you do the calculation, you'll find out to get 45-degree rotation, you can achieve that with just centimeters of fiber. Centimeters of this material. But if you want to do the same rotation, if you want to achieve the same rotation in fiber, then because the Verde constant is so low, you have to compensate that with L. But that's not too difficult, because in a fiber, just like we did for this fiber optic gyroscope, we were actually getting a scale factor in terms of the response by the fact that you have a number of turns in your, you can make a coil out of your fiber and you have a number of turns in your fiber. So similarly, you can actually have a very long fiber, and through that you can sort of compensate for this fact that this V is relatively small. But nevertheless, in terms of detecting this, we do what we did previously, right? So we have this polarization beam splitter that is actually picking up this orthogonally polarized components, and then you take them into a balanced or a differential circuit, and then you can get your current I, so this has to be differentiated with respect to this current here. So this is let's call this ID, that corresponds to the current that's detected. So essentially you can say that depending upon this current, you have a magnetic field, and that magnetic field rotates this polarization, and that polarization changes the power distribution between these two detectors, and then you can actually see that power change or measure that power change in terms of the photocurrent, and then maybe you can put a transimpedance stage beyond this to convert that to a certain voltage, and that's how you establish a current sensor. Okay, so there are some very interesting aspects of this. this is actually highly sensitive to current. Of course, you can go back to this discussion and say that your best operating point is here. So instead of having a polarizer just giving you vertical polarization, you can send in 45-degree polarization, and that may be your and look for changes in theta with respect to that. So you start with 45 degrees and you look for changes with respect to that to get the best sensitivity. But yeah, all that you can do to improve the detection, but the basic scheme is based on this Faraday effect. Okay. Now I'll just leave you with this thought. One interesting aspect about Faraday effect is it's a non-reciprocal effect. So this is actually what is called a non-reciprocal effect. So what do we mean by that? Now if you come back with the same polarization in the opposite direction, if it is a reciprocal effect, you would get this linear polarization output, right? But because it's dependent on the orientation and the direction of this incoming electric field, if it's coming in the opposite direction, it doesn't go back to the original stage. Instead, it goes through twice this theta, right? So you go one way in forward direction, you get theta, but when you send it back, you get actually twice theta. So why is this important? Well, it's important because you could get changes in this theta because of a lot of random birefringence that you have in the fiber. Okay, but the key point is all those random birefringence, because of some external perturbations, you can have random birefringence and you can have changes in theta. But all those random birefringence would cancel if you actually put a reflector here and send that light back. Okay, it will all cancel out, and what will be remaining is actually the this non-reciprocal Faraday effect based rotation, and that is what is going to be the thing that you can measure. So that is actually what is called reflected or it's called a reciprocal reflectometer configuration, and that's something that we will look into a little more detail in the next lecture.